Hello everyone. Today we will be discussing about the dissolved oxygen present in any water sample or wastewater sample. Let me share the screen. Aim to find the quantity of dissolved oxygen present in the given water sample by Winkler's method. Let us know about the principle. What is dissolved oxygen? It is the amount of oxygen which gets dissolved in the water. The oxygen present in the sample oxidizes the divalent manganese to its higher vacancy, which precipitates as a brown hydrated oxide after the addition of manganese sulfate and Ki. So in this experiment, we are using MnSO4 solution, that is manganese sulfate solution, and potassium alkali azide solution. So when these two are added to the sample, they oxidize the divalent manganese ions. Upon acidification, the manganese reverts to divalent state and liberates iodine by reacting with potassium alkali azide solution. Next, this liberated iodine is titrated against sodium thiosulfate of 0.025 normality using starch as an indicator. If oxygen is absent in the sample, the manganese sulfate reacts with the alkali to form white precipitate, that is manganese hydroxide. Coming to the theory, so what is dissolved oxygen? As I already told, it is the amount of oxygen dissolved in any water or in the sewage, wastewater, and this particular content of dissolved oxygen indicates whether the sewage is fresh, stale, or septic. The solubility of oxygen in the water depends upon the temperature because at the surface there is always exchange of gases. Oxygen which is present in the atmosphere gets dissolved in the water at the surface where there is exchange of gases. This dissolved oxygen is very important in the precipitation of inorganic matter and oxidation of organic and inorganic matter, what we call BOD, biochemical oxygen demand. So it is the amount of oxygen which is required to decompose all the organic matter present in the water or wastewater. This oxygen required for the decomposition of organic matter, inorganic matter, is usually satisfied when there is sufficient amount of oxygen dissolved in water. The dissolved oxygen should be known to determine the quality of raw water. It helps us to check the stream pollution. The dissolved oxygen should always be maintained at a level of 4 to 8 mg per liter. If this dissolved oxygen is less than 4 mg per liter, then it will seriously affect the aquatic organisms. The aquatic organisms which live inside the water and they breathe the oxygen which is dissolved in the water. If this amount reduces, then it may not allow the survival of these aquatic organisms. It also may hinder the growth of plants, that is aquatic plants, aquatic weed growth, aquatic algae, which need oxygen. They also may suffer due to lack of dissolved oxygen. Moving on to the environmental significance, we know oxygen is poorly soluble in water. Its solubility is just 14.6 mg per liter. For pure water at 0 degrees Celsius, its solubility is 14.6 mg per liter under the normal atmospheric conditions and the pressure, and it drops to 7 mg per liter at 35 degrees Celsius. When this free oxygen is available in plenty, available in sufficient quantity, the aerobic bacteria thrive. Whenever anaerobic conditions prevail, when sufficient DO is not available within the water, it reaches anaerobic state. Here the end product of aerobics are stable and are not foul smelling, but the end products of anaerobic are foul smelling and they are also unstable. A minimum DO of 4 to 5 mg per liter is desirable for the survival of aquatic life. Higher values of dissolved oxygen may cause corrosion of iron and steel. At higher temperature, the biological impurities, ammonia, nitrites, ferrous iron, chemicals such as hydrogen sulfide and organic matter reduces the DO level. Whenever there is growth of algae, it adds oxygen to the water. And one most important thing is the drinking water should be rich in dissolved oxygen. When drinking water has sufficient amount of dissolved oxygen present in it, it imparts a good taste, a good aesthetic appearance. It will be bright. That plays a aesthetic look and a pleasing effect. Moving on to the applications, it is necessary to know the dissolved oxygen levels to assess the quality of raw water and to keep a check on the stream pollution. Because when DO is in sufficient quantity, the water will be in a sparkling blue. So we can say it is fresh. But the water which has less DO will not be so appealing. DO test is the basis for BOD test, that is biochemical oxygen demand. Because in this biochemical oxygen demand, we determine the initial DO content, and after 5 days of incubation, we determine the final dissolved oxygen content. And the difference between the DO, that is the dissolved oxygen level, gives us the BOD. At 5, after an incubation of 5 days at 20 degrees Celsius. So DO test is the basis for this BOD test, which is an important parameter to evaluate the organic pollution potential of a waste. Oxygen is an important factor in the corrosion of iron and steel. DO test is used to control oxygen in the boiler feed water. Dissolved oxygen test is necessary for all aerobic biological wastewater treatment processes so that we can control the rate of aeration. DO test is used to evaluate the pollution strength of domestic waste as well as industrial waste. Determination of DO in wastewater is very useful to identify the nature of biochemical reactions, which means when we understand the nature, we come to know whether the reaction is aerobic or anaerobic. So whenever it is an aerobic reaction, it gives out stable end products. And these stable end products are carbon dioxide and water. But at the same time, when an aerobic reaction prevails, there is a foul smell and the end products are unstable. This is mainly due to hydrogen sulfide, H2S. Moving on to the apparatus which is required to perform this experiment, we need burette, pipette, conical flask, BOD bottle, which is very important, and measuring jugs. The reagents required are potassium alkaline azide solution, magnesium sulfate solution, concentrated sulfuric acid, sodium thiosulfate of 0.025 normality, and starch indicator. Moving on to the procedure. So the BOD bottles of 300 ml capacity are available. We need to take a 300 ml capacity BOD bottle. The given sample has to be filled in this bottle. When you fill the bottle, you should see that there are no air bubbles present or they are not going to be developed. Once it is filled, you need to close it and remove the excess amount of the sample. The next step, you need to remove the stopper or the lid. Add 2 ml of MnSO4, manganese sulfate solution. Shake it well. Turn it upside down. Then add 2 ml of potassium alkali azide solution. One most important point when we add manganese sulfate solution and potassium alkali azide solution, you should see that when you are adding it, the tip of the pipette should touch the bottom of the BOD bottle. Once it is added, slowly you need to remove the pipette. Next, close the stopper. Turn the sample upside down so that it mixes up properly and the excess amount is discarded. After potassium alkali azide solution and manganese sulfate solution are added, the next step is to add concentrated sulfuric acid. We add 2 ml of concentrated sulfuric acid in the same manner. That is, again care has to be taken such that the tip of the pipette touches the bottom of the BOD bottle. And slowly you add concentrated sulfuric acid. Once it is added, you are going to remove the pipette, close the stopper, turn the bottle upside down 2 to 3 times so that proper mixing is done, and you keep this bottle for settlement for a period of 2 to 3 minutes until the suspension is completed. After 2 minutes, you have to observe the color. It is usually dark yellow or pale yellow. Once the sample is dark yellow, you need to titrate it against sodium thiosulfate of 0.025 normality till it becomes pale yellow. So the titrant is sodium thiosulfate of 0.025 normality. Once the sample turns pale yellow, you need to add starch indicator. As you add starch indicator, the sample turns blue. This sample has to be further titrated against sodium thiosulfate of 0.025 normality till it becomes colorless. One most important point is that from the BOD bottle, you're going to measure 203 ml and place it in the conical flask. After you measure 203 ml in the conical flask, you're going to proceed with the titration. You're going to add starch if it is pale yellow. In case it is dark yellow, you're going to titrate. You're going to note down the initial burette reading. You're going to titrate from dark yellow to pale yellow. You're not going to note down the intermediate reading. Once the sample is pale yellow, you're going to add starch indicator. The sample turns blue. You're going to proceed with the titration. You continue. You start titrating till blue color vanishes and you have a colorless solution. You note down the volume of titrant added, the final burette reading. So you have to tabulate it in a tabular column, initial burette reading, final burette reading, and volume of titrant added, FBR minus IBR. So this gives us the volume of titrant, that is sodium thiosulfate added. So you can note down the volume of sodium thiosulfate added as V in ml. So you can see the figure here. This is the burette stand, conical flask. So the titrant is filled up in the burette. We have sodium thiosulfate of 0.025 normality, that is the titrant. And in the conical flask, we have a sample where you have added 2 ml of potassium alkali azide solution, 2 ml of manganese sulfate solution, and 2 ml of concentrated sulfuric acid. So this sample is transferred from the BOD bottle to the conical flask. We measure exactly 203 ml and place in this conical flask. You will observe the color. If it is dark yellow, you need to change it to pale yellow. But if it is pale yellow, directly you're adding starch indicator where the color turns to blue and you are titrating till it becomes colorless. But in case you get dark yellow, you need to write down the initial burette reading, add titrant, titrate it till it becomes pale yellow, then add starch indicator, it becomes blue. Then you further titrate till it becomes colorless. So the end point is blue to colorless. So partially first part, it is you observe whether it is dark yellow. If dark yellow, make it pale yellow. Then add the indicator starch. So the end point is blue to colorless. You note down the final burette reading as VM. Next, you proceed on with the calculations. Therefore, dissolved oxygen is equal to V, volume of titrant added, into equivalent weight of oxygen, into normality, into 1000, divided by volume of sample. In various experiments, we will be taking the volume of sample as 50 ml or 100 ml. But in this particular experiment, we are measuring a sample of 203 ml and we are titrating it. This method is known as Winkler's method. So once you calculate the volume of titrant into equivalent weight of oxygen into normality, 0.025 normality, into 1000 divided by 203, you get the dissolved oxygen in mg per liter. You have to note down the result of dissolved oxygen as mg per liter. And finally, you have to compare with the standards where a permissible limit is 4 to 8 mg per liter. Minimum of 4 mg per liter is required for the survival of aquatic organisms. So once you obtain your result, you're going to compare with these standards and you're going to conclude whether the sample has sufficient amount of dissolved oxygen or not, and whether it is fit for domestic purpose and whether the aquatic organisms can survive. In this way, finally, we'll be concluding about the dissolved oxygen content. Let us move on to some Viva questions. So what is dissolved oxygen? How does the dissolved oxygen get depleted? Foul smell prevails under which conditions? Upon acidification, which gas is liberated? What are the applications of dissolved oxygen? Explain the environmental significance of dissolved oxygen. Which gas is liberated under anaerobic conditions? What happens if the dissolved oxygen depletes? What is the permissible limit of dissolved oxygen? Which are the stable end products in aerobic conditions? Thank you.